and he's going to talk about the TCC states.
Okay. Can you see my screen first of all?
Yes.
Okay. Yes. Okay. Full screen. Okay. So first of all, thank you to the organizers for allowing me to present this talk in this conference. So as Raquel was saying, I'm going to talk about the TCC state, a couple channel analysis. So since there has been a lot of presentation of this state in the morning session, I won't go into a lot of details about that. But I would like to first have a general picture about the situation here. So if we think about the predictions of the quark model in the singly heavy sector in the open charm, single open charm sector, you see that still quark model allows to classify most of the states, right? These are, for instance, predictions for the charm strange and non-strange sector that was discussed a few minutes ago, indeed. And you see that the states that are found are usually can be easily ascribed to some of the predictions of the quark model. And as soon as you have states that are close to the thresholds, in the left, for instance, in the DK or D*K threshold, things are not so easy. So when you have states close to thresholds, then the predictions are not, the experimental findings are not so easily classified in the quark model. Okay. And of course, something similar happens in the charmonium sector with the X3872, which were discovered roughly at the same time. So in particular, of course, the double charm sector is also very interesting because of its explicit exoticness. In this sense, the TCC, the constituent quark flavors are CC, U bar, D bar. And there are a lot of predictions across time with a broad range of predictions. And about lattice QCD, it seems that the prediction in the charm sector is not very conclusive, but it is in the bottom sector that there is a state analog to this one. And last year, LHCb comes out with these two papers in which they analyze this spectrum, in which they see a clear peak, prominent peak near the D*D thresholds. Okay, and this is the peak I'm going to analyze in this work. Just one word about the nomenclature in this tetraquark thing. When we say the nomenclature that has become standard by now is that the picture you see on the right here, it's called a compact tetraquark, whereas the left one is called a molecular tetraquark. Okay, so whenever I say tetraquark, because it has become standard, I will refer to anything that has 4 quarks as a flavor. There is a nomenclature which would be more natural, but it's not standard right now, which is to call compact tetraquarks, call them simply tetraquarks, and what is called a molecular tetraquark, call them simply molecule. Okay, but it is what it is. Let me discuss my production model. So from the picture, from the data of LHCb, what I see is that the spectrum is basically the TCC signal and some background which seems to start around the D*D threshold. So it seems reasonable to assume that all the DPi events are produced through D*D, because of the background starts at that threshold. And also because of the small range in the DD-pi invariant bands, it's reasonable also to assume D star D are in S wave. Okay, so this is all I have in my production model, and everything is parameterized in terms of two coefficients alpha and beta, which parameterize the strength of the production of the two different channels. Once you have that, the event distribution is straightforward to compute in terms of that amplitude that I am making here. And also, just let me say that in this model, I am adding this diagram, so I have what you would call background terms here, in which there is in principle no necessarily D star D scattering, and also the rescattering here, the red squares that will contain the D star D scattering amplitude that I'm going to discuss next. So I set up a couple T matrix for these two channels. The idea here is that the D star Ds are decomposed into isospin states, so the potential or interaction kernels can be easily written in terms of two different coefficients that represent isospin 0 and isospin 1 interactions. And the G functions carry the loop functions of each of these channels. That thing can be computed analytically, and to include the D star width, which is important here, I continue them analytically in the D star mass to the complex plane, and in that way I have an estimation of the effect of the D star width. For the cutoff, I use two different values which represent essentially the momentum at which you cut the interactions. The V matrix elements depend on the cutoff, but this is something that it's usual in the effective field theory approach. Okay. So basically, I have then two parameters modeling the production amplitude, two parameters modeling the scattering amplitude, and of course one global normalization. One of the parameters modeling the production amplitude, of course, can be reabsorbed in the global normalization constant. So in the end, I have three parameters and one global constant. Okay, this is what I fit, and I found in both fits I found good agreement with the data, as you can see in this figure, both in the 0.5 beams, and also in the other data that the LHCb provides every 0.2 MeVs. Also, the pool of the data, meaning the difference between data and experiment with respect to the experimental error, is also randomly distributed, so there are no structures there, which also is good from the statistical point of view. And the errors here are obtained with Monte Carlo bootstrapping of the data. Okay, so and that is propagated everywhere in every quantity I give here as an output. In what refers to the spectroscopy, I find a bound state pole. First of all, here in this plot, I'm in this top plot, I'm plotting the determinant of the denominator of the amplitude. This plot is similar to the one that the LHCb has in the second paper, and you see that the real part goes through zero below threshold. Okay, the real part. The imaginary part is not zero because you have some width, so that means that the pole is close to this position, but not exactly at that position. Okay, this lower plot is similar to the one that Eulogio was showing this morning from their paper with Feijóo and company, and it is the unconvoluted or not convoluted spectrum. Okay, so this is your, let's say, original prediction if you don't take into account resolution. Once you take into account resolution, then you have the experimental distribution of events. So going back to the pole position, I find a very similar position of the peak, very similar to the LHCb analysis. The width in my case is larger than the one from the LHCb, but it is similar to the one that these people here, Menglin, Juan, Christoph, many people in the audience actually, as authors of this paper, they have also this width. They use several models. One of them is similar to mine, and in that case, both results agree. They are very similar widths. So the question, of course, is what type of state is this? From the Weinberg compositeness condition, which you have been hearing all morning. So what I find is summarizing in the isospin limit from the computing the probability from my amplitude, I have that it is a purely molecular state, but that's something that is already built in the model, right? Of course, the probability in my case has to be 1, so it's not very telling, the fact that I get probability 1. But if now I compute in the isospin limit case, I compute the scattering length and the effective range, I can compare with Weinberg compositeness condition for A and R, for the scattering length and the effective range. So this is what I'm plotting here. The red line is the Weinberg prediction for the scattering length and for the effective range in terms of the Z parameter. And you see that naturally the closer Z is to 0, the closer the scattering length is to the one I obtain from my computation, and also happens the same in the effective range. But you could also say that still the radius is 0, or it's not negative because I get a positive radius, or that the scattering length is a little bit far away. If then I use the nextly in order relation that Juan Nieves and myself have recently worked out, I can do the same calculation for this. Basically, this thing, these relations correlate the corrections in the effective range with the correlations in the scattering length. I don't want to go into details of that. But
Miguel,
then,
you have 3 minutes.
Yes, thank you.
Miguel, sorry, we don't see the x-axis in your figures. X-axis, I think is Z, right?
You don't see it? I see it.
Sorry, okay.
Raquel, you see it?
Fine.
Yes,
I can see it.
I can
Yes,
see
we
that.
can see it.
Okay.
Fine.
Then if I use some value for this correction of the range parameter, you see that indeed, of course, I can get the radius be the one that I compute from the T matrix, and then at the same time, for the same price, the scattering length comes very close to the one that you have from let's say, it's not experiment, but it's the one I get from the T matrix. So basically, the message is that C is very close to 0, and then you call that a molecule. So I can also make predictions for the heavy quark because of heavy quark spin symmetry. States for D star threshold. Okay, so assuming that this state TCC is isoscalar, you get another isoscalar state close to D star threshold. Instead of being bound by only 0.4, it's something like between 1.5 and 1 MeV. If this TCC, it doesn't seem to be, but if this TCC was an isospin 1, then you would get a D star 2 plus state, and it would be a triplet, okay, with similar bindings here. The prediction for the isoscalar is similar to the one by Raquel and Eulogio in recent papers, and also they had already made some work on this a few years ago. So just one final word is that so the question of the compositeness could be addressed in a different way, which is, and this type of form factors are going to be computed sooner or later by lattice QCD, in which you study which is the size of anything that you call a tetraquark, okay, and then you can see if you are losing the wave functions of the components or not, and then you could say if something is a molecule or not. This is just a comment. So in summary, we keep living excited times in hadron spectroscopy, because there is always every now and then very exciting discoveries. In this work, what I've done is an analysis of the T-matrix coupled channel for the 2 states in which one expects the TCC. If I've done a simple production model and a simple scattering model, and which allows to see the TCC as a bound state that I found to be largely molecular, and also from this calculation, one can make a prediction for a D star state, either isoscalar or isobector, not both of them. And also I've been comparing with other earlier and later theoretical works, and there is found agreement in different aspects of this work. So thank you very much.
Okay, thank you, Miguel. We have already a few hands raised. So, Poliaco,
Yeah,
please
hi.
go ahead.
Thank you. Miguel, thanks for the talk. Can you please go to the slide 5, I think, where you have your feet.
Feet here, 6.
Yeah, so this is, sorry. So first of all, as I understood correctly, from your result, you're saying that there should be isospin 1 coupling there. So you claim that it's significant, right?
There is some coupling, yes, but the point is that the amplitude is mostly fixed by the peak, right? And that fixes the C0 parameter. So all that is not the C0 parameter is less constrained. And because there are also mechanisms that could be here that I'm not including. So in a few words, the C0 parameter fixes the peak, and that I trust. Every other parameter must be taken with a grain of salt, I think.
Oh, okay. So we should not look for the numbers for the C1, right?
Mm-hmm.
Okay, good. That was one of my concern. And secondly, I'm kind of surprised a bit that on the feed there is a dip around the second threshold. I'm wondering how you could get that after, like, if you're already smearing your peak with resolution. So it's kind of strange how I can get such a dip.
I think that this dip is also in other works. I mean, there is.
Well, when we have made the original paper, we see such a dip if it's before convoluting with the resolution, it exists, but after you convolve the resolution, like we don't have anything.
Probably depends on how deep is your how deep is your dip.
Well, I
before convolution.
I think in our work it was like going almost to 0, but after convolutic resolution it's just there. So the related question is, when you model the background, it's the 2-body phase space, right? But is it the D0, D star plus. So it's starting from the first threshold, does it?
So when you say model, the background, it is the sum of these diagrams. I mean, I don't add a explicit
okay,
term.
so it's not two different terms, it's the interference.
Yes.
I see. Okay.
But coming to the second part of your question, yes, it starts, that kind of contribution starts in this star D threshold.
Okay, but it's not just the sum, it's and the thing on the right, sorry, on the next slide 7, this shape, is it also already takes into account this non-resonant contribution?
Yes, this is everything together. Yes, it's the same full spectrum.
Okay, thank you.
Okay, so Christoph Hanhar.
Hi, Miguel. Thanks for the nice talk. Can you go to page 8, please?
8.
I now make a statement. I would like you to answer if you agree that this is indeed what this calculation tells us. When I look at the value of R as a function of the cutoff of the table on the middle right, I see that the effective range is strongly cutoff dependent, which shouldn't be surprising because the effective range in your calculation really emerges from the p-square dependence of the loop. Yes. Therefore, my statement that I would like you to comment on would be that your calculation basically shows that the data is consistent with a positive effective range, but that you cannot really pin it down yet. Would you agree?
Totally. I mean, I think that you've summarized better than I could.
Thank you very much.
Okay, I think Sasa, she also has a question.
Yeah. Well, thanks for a nice talk. You mentioned also lattice simulations. Of course, for TCC, so much has not been done as for TBB, but I would just like to mention that recently Padmanabh and me, for the first time, found the pole related to double-chum tetraquark in lattice simulation. I mean, it seems to be likely related to the TCC. So the pole in the DD star scattering amplitude, so that was published in the end of February. So it's just a comment.
Yeah. I mean, I didn't go into details about
sure
references. I just meant that, I mean, there are different works with different conclusions in the charm sector.
No, but I mean, never so far the pole was extracted, right? There were just the energy levels, but for the first time the pole was extracted.
Okay, that's true. You're right.
Okay, thanks. But at unphysical biomass, that's also true.
Okay, if there are no more questions, let's go to the last talk of this session.
Thanks, Raquel, for the announcement, and thanks to the organizers for allowing me to give that talk. So for my rationale in preparing this talk was to basically give the grounds for the discussions that will follow right after. So for the references I show here are those that I will be referring to in going along, and the authors of those references are also the co-workers that I am grateful to. So to set the stage, what is this all about? If you want to go from line shapes to the nature, the essential information in that will really be that it gives us a handle on the distinction between extended objects, which are formed from color neutral objects, which can be very large if the location of the corresponding pole is very close to the continuum threshold, compared to something that's compact. Therefore, from what I will be telling, we will not be able to disentangle what this compact stuff is, similar to what Luciano already said this morning. Therefore, to distinguish from this Weinberg point of view, Quarkonia, or say tetraquarks is impossible. The only thing it can address is how large is a molecular component. And the reason why that gets possible is because this the state formed from two color neutral objects have the special feature that they have unitarity cut, and that introduces a scale that's non-analytic in the energy, and that's unique to molecular structures and cannot, as a matter of fact, appear in quarkonia and tetraquarks. And this is what the Weinberg criterion basically measures: the significance of this analytic, non-analytic in energy scale here, and that allows access to the compositeness. Okay. What I would like to do here is I want to rederive the Weinberg criterion, and here in particular put emphasis on where the uncertainties enter, on how large they are. Therefore, the whole analysis starts, as Luciano already mentioned, from a couple channel ansatz. We have some compact component where we will not be able to tell what its meaning is on the one hand. On the other hand, we have a 2-hadron component, which is characterized by its wave function. Now, lambda here, as it appears, is obviously directly the overlap of psi naught, this compact component with the full physical state. Absolute square is lambda square, which in the full spirit of non-relativistic quantum mechanics is nothing but the probability to find this, well, here I call it bare state, before I called it compact state, in the physical state. Therefore, if you're able to measure lambda square, we have a direct measure of the composition of the wave function. Actually, the famous Weinberg paper where this Weinberg criterion was defined was not the first paper where Weinberg addressed the issue of hadron-hadron interactions. Actually, this was the third one of a series. So 2 previous ones are these. And here he showed a very important thing that is often missed in the argument. What Weinberg showed in these 2 papers is that a non-perturbative hadron-hadron interaction that produces a pole is actually equivalent to a pole term plus perturbative interactions. Therefore, no matter how complicated the potential is, as long as we stay close to the pole, one can equally model it by a pure pole term. All dynamical information then is transferred into the couplings. Therefore, that we describe a state by a pure pole term does not mean it cannot be a molecular state, simply because of this famous equivalence here. But it just means that if it is a molecular state, the couplings, for instance, take certain values, and these certain values of the couplings gets transferred to scattering length and effective range, as we will see. Now, how does the derivation go? Having said that, the meson-meson interactions can be in leading order neglected, the hadron-hadron piece of the full Hamiltonian only contains the kinetic terms. This is not an approximation in the spirit of neglecting hadron-hadron interactions, as I said before. It simply acknowledges the fact that this pure pole term distribution captures all the physics. Having this Hamiltonian and the wave function ansatz from the previous page, we can solve for the wave function. That's what we get. Introducing that now, we get therefore for the full wave function this nice and compact expression. It contains lambda, our parameter of desire. It contains f of p square, which is defined as a transition form factor from the 2-hadron component to the compact component, and it contains a binding energy, and that's it. There's nothing more in this. Now we need to demand, since this is supposed to be a bound state, we need to demand the normalization condition. Therefore, the absolute square of this thing must be 1, and that directly gives a relation between lambda square and the mentioned hadronic parameters, transition form factor, and binding energy. Therefore, if you understand what this integral means, we can derive a relation, and this is what the Weinberg relations are. So we have a closer look at this integral, and we observe that we can just evaluate that integral analytically up to corrections of the order binding momentum over range of forces. And what enters here is basically the transition form factor at 0, which we will eventually call the coupling constant. Now, therefore, what goes into here is basically the observation that this integral here is p to the 4th in the denominator, p cubed in the numerator, even if the form factor is a constant. Therefore, the estimate for this uncertainty comes from the fact that from the assumption that we can assume that the integral is already converged by the denominator before a change in the numerator sets in. But that sets the scale of the corrections here. Therefore, all those improvements that Eulogio and Miguel alluded to in the course of the day are basically estimates to attempts to estimate this contribution. However, the Weinberg statements as such persist up to corrections of that order, which might be improved upon. Now, putting this integral in, using that definition for the coupling, we get a very nice relation between lambda square and g square, which can be rewritten in terms of g square. And if we get the access to g square, we get an access to lambda square, and we are done. Well, this thing here has a peculiar feature. G square goes to infinity when lambda goes to 0. Therefore, it sounds like an infinite physical parameter. That doesn't really make sense. One should keep in mind, however, that this g square here is an unrenormalized parameter. Therefore, the residue at the pole is lambda square g square up to some normalization factor. And lambda square g square clearly is well behaved. It goes to its maximum value, which is given here when lambda goes to 0. Lambda square goes to 0, and it goes to 0 when lambda square goes to 1. So this is one way of writing the Weinberg criterion. Therefore, 1 minus lambda square directly quantifies the molecular component in a physical state. The important conclusion to draw from what I've just said is that the structure information is hidden in the effective coupling, which can be extracted from the experiment, and that's completely independent from the phenomenology one uses to introduce a pole. At the end of the day, after renormalization, and fitting to data is nothing but taking into account the renormalization. At the end of the day, the physics is sitting in the effective coupling. Okay, now let me make the contact to the effective range parameters. Therefore, one way to start from is to express the scattering amplitude directly in terms of the binding energy and the coupling, as I had before. That's how the scattering amplitude reads. To remind you, this is again the unrenormalized coupling. So if a g square gets infinite for a molecule and 0 for a compact state. Now we can compare this expression to the effective range expansion. We can directly read off the relations between of A and R and lambda square and gamma. Those are the relations you've seen already in several talks today. And the corrections range with the to both expressions scale with the range of forces, which can be identified in most cases with 1 over beta, where beta is the lightest exchange particle. Okay, now one can even generalize this. This thing was tried by many people. I will here just allude to the stuff that we did, because to my understanding, we are the first to focus really on virtual states. So what does the Weinberg criterion tell us? As Luciano nicely explained, typically the effective range is positive. So this plane is a scattering length effective range plane. Typically in bound states, the effective range is positive. I will tell you when exceptions emerge. And for the Weinberg criterion and the sign conventions we have, for bound states, the scattering length is large and negative. And for a compact state, the effective range is negative and large, and the scattering length is negative and small. Therefore, one might now ask what happens if one slightly changes the parameters. Therefore, we can, for instance, play games with quark masses, as Sinnert alluded to. What then happens is usually that the state gets unbound if one, for instance, makes the quark masses lighter. And then what happens is that in case of the, if we just do an analytic continuation of the Weinberg expression, that this here jumps over here, because typically when slightly changing the quark masses, the scattering length changes more than the effective range. Therefore, in first approximation, we can assume the effective range stays constant. Therefore, the bound state turns into a virtual state, but the molecule turns into a virtual state, while the compact state immediately goes into a resonance. That's an important takeaway message. So far, this relation that a virtual state is a molecule was always quoted, but to my knowledge, never made contact to the Weinberg criterion. This is provided in this paper. A compact form for the compositeness that actually captures these features that is shown in this picture is that one takes was a composite 1 over square root of 1 plus the absolute value of 2r over a, because when a changes sign and r stays with the same sign, otherwise the Weimar criterion leads to strange results, but putting the absolute value here really captures all those features nicely. Now let's come to applications. KC1 3872, also known as X3872. You've heard a lot about this already in the previous talks. Also, these pictures you've seen. If one fits the data with a Flatté or with a Breit-Wigner, once the resolution is put in, the lines are basically getting indistinguishable. It's my understanding that the log likelihood here rises from the Flatté fit of the LHCb analysis, mainly because there was a constraint built in that the most prominent decay channel of the X is the DD star and not the other channels like rho J psi and omega J psi and whatever is there in addition. This makes this thing rise. The data themselves cannot tell apart if even the effective coupling is 0. Okay, what was used in the analysis is a parametrization that we've proposed a couple of years earlier in 2007, which you see here. It contains a contribution from the neutral channel, it contains a contribution from the charge channel, and the imaginary parts from the other channels. Moreover, already in 2007, we suggested, which was picked up by the LHCb collaboration, to put these couplings equal, which implements then that the 3872 is an isoscalar state. And then one finds the correlations here that Luciano already mentioned, which basically demonstrates that the coupling here is very badly determined by the data. If one reads off from this parametrization now the effective range, one finds from this formula straightforwardly the two contributions that Luciano already mentioned. There's one piece which scales with 1 over g square. There's one piece that's related to delta, which is the splitting between the neutral and the charged DD star threshold. And one finds indeed a negative, oops, there's a minus missing here. Oh, no, I show minus r, sorry. One finds a large and negative effective range, which is much larger than 1 over m pi. And in this paper here, as well as in Luciano's talk, from this observation, it was concluded that the X is a predominantly compact state. I would like to question that in my talk. Well, the reason mainly why I question that is because the term that indeed survives once we assume that this coupling is very large. About this coupling, I will talk on the next slide. Therefore, let's see, focus on the blue term. That this term really comes just from the isospin violating contribution. Therefore, to get to this term, what one does is here to expand this expression in in energy over delta, because we lie very close to the D0 star threshold and relatively far away from the charge threshold. So this is what you get when you expand that square root. And indeed, a term emerges that scales with 1 over square root delta, 1 over square root of the mass split in between the neutral and the charge channel. Moreover, what is very important, I told you that in the molecular scenario, G square goes to infinity. G square, which would, let's assume this state would be a D0 star threshold, which would be here just G1 square. G1 square to infinity, while keeping G2 square finite, completely eliminates that term. Therefore, the reason why we get that sizable contribution here in the final analysis, where G square is not constrained, was because isospin symmetry was imposed in the analysis in the coupling. So that removes this ratio here, and we are stuck with that contribution, right? Moreover, delta going to 0, which would be the isospin limit, is actually making this term here explode. Therefore, this term does not measure the contribution from the compact component. It basically measures the contribution from the charged component. And what we see is that the X properties measured so far is completely consistent with an isoscalar state. In a model-independent analysis, one has no choice but to abandon this. because simply we cannot switch off all isospin violating contributions. As soon as one imposes a model like Miguel presented, he can go to the isospin limit and make his investigations there. Then also this term would have gone completely, because in this parametrization in the isospin limit, these two terms agree because delta goes to 0, and then we have only a single term here. Therefore, if anything persists from the effective range, here it's that term. But we come to that term, Luciano already alluded to that there is a very flat minimum here. So basically G square is not really constrained. But we can say more. If we look at this parametrization here, everything that's put in red basically fixes for a bound state, for a pole below threshold, basically just fixes that pole location. Therefore, we can argue that everything that's given here can be written as fixing the pole location in terms of these parameters. If we now calculate here the two square roots, again, in terms of the same EP that's now put here on the left, that immediately gives a correlation between this parameter here in the original parametrization and EP and G square. In particular, G square emerges as a function of EF and EP. EP being a physical parameter that's well constrained, EF being a parameter artifact of the original parametrization. And indeed, if we acknowledge that EF is actually much smaller than, that EP is much smaller than delta, in leading order, we get a parameter-free prediction for that correlation. And this is put here as a solid line. This really shows that this correlation can be very well understood directly from the original parametrization. One can even go a step further and fit EP from the correlation. And indeed, we get a number out, which is 27 keV, but this is not reliable because the points in the analysis here are correlated. Therefore, what needs to be done is to redo the LHCb analysis, acknowledging this correlation. And we have suggested in our recent publication a parametrization that can do that, which is actually given here. Therefore, in addition to the terms that were shown in the previous slide, one has to subtract the binding momenta at the pole. And as soon as one includes that, the correlation will go away. And this kind of parametrization is currently being used in a reanalysis of the LHCb data. I put here deliberately plus minus. The minus refers to the X emerging really as a bound state, as a first sheet pole if all other inelastic channels are gone. The plus would refer to a virtual state pole. I've mentioned virtual states before. Therefore, if the fit calls for positive values of EP, one should redo the fit with the other sign here, and those positive EP values will actually then need to interpret it as virtual states. Taking all this together, we need to conclude that the LHCb data only provides a lower bound of G. The second term that contribute to the effective range basically allows us to conclude that the current LHCb data only provides an upper bound, no lower bound to minus the negative effective range. And using that in the formula I advertised before, we get that the composite net of the X is larger than 0.94. Similar numbers emerge for the TCC state. I don't have time to talk about here now, but Miguel did. Now, how do we get a positive R? That is something that Luciano alluded to. Well, as I explained to you extensively, all the Weinberg formulas were derived neglecting finite range corrections. There's a famous bound already derived in 1955 by Wigner, which is called the Wigner bound, and is a consequence of causality, which requires that positive effective ranges need to be at most of the 1 over beta, which is the range of forces. Effective ranges larger than the range of forces and positive violate causality. Therefore, if I start from a model where I basically assume that exchange particles are infinitely heavy, I should only get at most a 0 effective range. Therefore, to get effective ranges that are positive, one has to invoke a model which actually includes the range corrections explicitly. Well, the longest range interaction that can appear is the 1-pion exchange. However, there's a problem. This 1/beta cannot be estimated as 1/m-pi in the charmed system, simply because if we are, say, at the mass of the X3872 or at the mass of the TCC, the pi dd bar or pi dd state can go on shell. If it can go on shell, it means that the pion, that there's a 3-body cut, and there's no fixed sign of the potential. Therefore, all naive estimates for the value of the effective range induced by the 1-pion exchange simply cannot apply. This applies for the deuteron, where the pion is always, the pion exchange is always space-like, there is no cut. Therefore, here the range of force is indeed 1/m-pi. In case of here, one cannot say that because there is a 3-body cut in the potential. However, one can get a feeling for what happens, but for that one has to employ some hadronic effective field theory. There are 2 versions out in the literature for treating heavy systems. On the one hand, there are people who prefer treating pions perturbatively. Calculations in that context, in an hadronic effective field theory. Lochio, I apologize for not mentioning you here, but I don't think you are doing an effective field theory. You are doing a phenomenological description. The people who propose in this effective field theory framework perturbative pions, the whole main players are Mian, Valderrama, Mikashenko, because he also pushes with JPEG for non-perturbative pion treatments, but the calculations that's out for the TCC is still perturbative pions. And non-perturbative pions are, to my knowledge, for heavy systems only done by us. Here are the main people involved in the calculations so far. And what we can do is we can look at the TCC calculation we've done and published in this paper with or without 1-pion exchange. If we compare the effect of the 1-pion exchange on the effective range, we see we get plus 0.4 Fermi from the 1-pion exchange. And we also find in that very publication, you can look it up there, if we switch off the corrections from isospin violation, similar in spirit to what Miguel proposed, and fit to the data, we actually indeed find a positive effective range for consistent with the data for the TCC, which has, in addition to this contribution, a similar cutoff dependent contribution that I asked for in Miguel's publication. But in any case, what is shown by Miguel as well as by us, the currently existing TCC data are fully consistent with a positive effective range. There is one issue I would not leave unmentioned when talking about the connection between line shapes and nature of the state. And that is, we get an additional handle experimentally if we have bound states with unstable constituents. This was first pointed out by Braten and Liu in 2007. And we've picked up their idea 3 years later, generalizing what they had also to more broad states. And this is what I'm referring to here. Therefore, if you have unstable constituents, the strength can leak to below threshold. What you see here is the dotted line on the left and on the right is what happens if you have a bound state or a molecule, sorry, with just with only stable constituents. However, if I now allow, the calculation is done for a bound state being located 0.5 MeV below threshold. Therefore, if the constituents are stable, clearly there is no signal below threshold. Therefore, if you do proton-neutron scattering, you don't see a deuteron, right? Simply because proton-neutron are stable and you cannot go below the proton-neutron threshold. However, as soon as the constituents get a width, in this case, the red line refers to one constituent having a width of 0.1 MeV, and the blue lines refer to a width of 1 MeV. You get leakage of strength of the amplitude to below threshold. And as that leakage starts overlapping eventually with the pole, which is located here at 0.5, you see a peak is emerging if the pole is on the physical sheet with respect to the constituents. And there is no strength below threshold if it's on the unphysical sheet, if the state is basically a quasi-virtual state. And the line shapes that emerges depends on basically the ratio of the constituent width to the bound state location. Therefore, if the bound state, if say this constituent width is larger than the bound state energy, you really get a nice peak, which is, however, highly asymmetric. We talked about asymmetric line shapes in the discussion session yesterday. If the bound state energy is of the order of the constituent widths, you can even disentangle the peak and the continuum. But be aware, this line shapes like this don't mean that there are two states in the data. It means that there is one state here strongly coupling to the continuum. You still get a two-bump structure, although there's only a single state here. And the reason is that by the Weinberg criterion, this bound state down here couples very strongly, actually couples maximally to the continuum. And this is where this strong shoulder here above threshold arises. Now, my final physics slide before I come to the summary. Now compare this thing here, this line shape that we sort of predicted in 2010 for bound states with unstable constituents to the data by Beth3, which emerged in 2014. I apologize to the Beth3 people that I forgot to put the reference. I should put the reference and then re-upload the my talk. What you see here is indeed a peak and a big shoulder. For this structure here is what is now called Y4330. And the line you see here is part of the PhD studies by Leon von Detten. It's in preparation for publication. This red line only contains a single state, Y4230, however, strongly coupling to the continuum. The bound state energy is 45 MeV, and the width of the constituent is 30 MeV. Therefore, this is similar to this situation of the red curve here. However, the situation in physics here is somewhat complicated because this narrow D1 mixes through spin symmetry violation into the broad D1, and therefore this direct connection between the width of the constituent and the relative height of the two peaks is sort of diluted. Okay, therefore, this brings me to my summary. Well, I forgot to mention here. Therefore, what I would like to stress here is that if one sees such a two-peak structure, not necessarily means that there are two states. However, what one can see here in the higher energy range, there is some systematic deviation of the data and the line. Therefore, there is most probably a second state up here, but it's not necessary to describe the bulk of the data. But this here is very close to the D1 D star and the D2 D star threshold, which couple again to 1-. Therefore, it's natural in the molecular picture to expect a second state up here. But as I said, there's a lot of work in preparation we will put to the archive soon. Well, this brings me already to my conclusion. Therefore, from what I said, from our point of view, and I think this will be further discussed in the discussion round, because there are people in the audience who do not agree to that. At present, the data on the KC1 3872, also known as X3872, as well as the TCC, are consistent with a pure molecular interpretation, but so far a sizable compact component cannot be excluded. To make more refined statements, we need to have a reanalysis of the X data with the mentioned correlations removed. I showed an expression that should be used for that. We need a combined analysis of inelastic and elastic channels, because then one doesn't anymore need to impose a constraint in the fit of the J-psi-pi-pi LHCb data, but one just directly fits the DD star channel, the J-psi-pi-pi channel. So this will lead to an even more refined analysis. Ideally, one would have a direct measurement of the line shape. And this is something where Panda has a promise. Again, here I forgot to provide a reference, but I think we anyway have a talk on this. But I will improve the talk and give the reference for the Panda estimates, how sensitive they are on the X3872 line shape. And finally, what contains a lot of information is isospin as well as SU3 partner states. I should stress very clearly, I don't have time in this talk to go into this. SU3 is an approximate symmetry of QCD. Therefore, I do not agree to Luciano's statement that SU3 multiplets only emerge in the quark model. In any theory soundly rooted in QCD, SU3 multiplets must emerge. But clearly, the SU3 multiplets that will emerge depend on the assumed underlying structure. And we already have some studies of SU3 states, especially the Spanish group around Juan Nieves has a lot of estimates on SU3 partners of molecules. There are isospins and SU3 partners for the molecules we've already studied. And looking into those, as well as the spin partner states, contains a lot of information. But to conclude my talk here, because this I didn't go into, is that the line shapes carry a lot of important structure information, especially on the molecular component. And there is also a lot of interesting and exciting stuff for states with unstable constituents, again, which I did not have time to put much weight into. Thank you very much for your attention. This is what I wanted to say.
Okay, thank you very much, Christoph, for a very nice talk. So we have a few hands raised. Ipoliako, please go ahead.
Sorry, I forget to lower it down.
Okay, Frank Nerli.
Yeah, hello. Thank you, Christoph, for this very interesting talk and also quite pedagogic. At least I feel I have understood quite some more details as before. Thank you for that. I have a question to your page 8, I think. Yeah, you had your line shape formula, which we also used, as you know, and I will come back to that tomorrow. You made the statement that there's an assumption going in, namely the X being isoscalar, and therefore the G1 is set equal to G2. This is interesting. Maybe I missed that before. My question is, what is the consequence in simple words on the line shape itself, or let's say to the outcome of the analysis by LHCb? If I understood from your later explanations, and this is clear also from the plot, which was discussed earlier also by the other talk in the morning, there is this correlation between the G value and the EF value, and this cannot, it seems to be resolved by LHCb. But probably that can be determined directly, independently by a direct line shape measurement as we plan it with Panda, correct?
Indeed. Therefore, what it boils down to at the end of the day is really the resolution of the measurement. And well, since you want to really explain that tomorrow in your talk, I don't want to take away the message, but the Panda has a way to significantly improve, say, the steps here in mapping out that line shape. Therefore, Panda should be able, if indeed the PB bar going to X3872 coupling is sufficiently large, to indeed distinguish the two line shapes, and therefore to get direct access to this parameter G, which will eventually provide which does directly provide a measure to the molecular admixture. Yes.
And then to the first part of my question, sorry, I was a little bit lengthy in phrasing it. What is the effect if we would not assume G1 equal G2 and then apply it in the LHCb analysis?
Speculate. My suspicion is, given what we see here in this picture, once the resolution is folded in, that if LHCb does an analysis with this term here completely removed, the fit will work equally well. I bet on that.
Okay, so the LHCb data is insensitive to this assumption.
I bet. Well, we know that the X is an isoscalar state from various other sources. Therefore, this assumption here was very natural at the time, and it still is. Therefore, the isospin violation really comes in basically through largely through the effect here from the cut. The best paper where I know this is where this is explained is a paper by Osset and Gammermann, where they nicely show that the ratio of the rho and omega widths is naturally explained by predominantly the effect that you have the isospin violation in the kinematics and not in the coupling.
Thank you for that explanation.
But the line shape as measured by LHCb will not be sensitive to the presence of this term.
Okay.
Okay, so there is another question by Feng Kung Wu.
Hi, Christoph. Thanks for the very, very nice overview. It's actually from my side, it's not a question, but just comment. I think if time allows, I will probably show a few slides on the discussion session. The comment is that actually the Weinberger's formula, although that has always been assumed that the uncertainty is gamma over beta, but actually it is more precise than that. The uncertainty would be gamma squared over beta squared for negative effect range.
I completely agree, but to see that, Van Koen has to work harder. Therefore, here for this simple explanation here, I could not say more, but agree. I recently also sent you this reference where we already in 2007 also found that the corrections are already of order beta square, gamma square over beta square, although at the time, we didn't really put too much emphasis to that. But from this naive analysis here, it is really gamma over beta, but I agree there are good arguments to assume it's gamma square over beta square.
Well, I think in that case, in our case, it's not really just argument. Yeah, it would be proof, because the order gamma over beta correction, well, that kind of effect has already been included.
Actually, in our publication, we also show that these effects actually do cancel. But let's come back to that in the discussion session, because it's a technical issue. But I completely agree with you. This is the most naive estimate, and improved analysis can show that this is actually even smaller.
Okay, so we have also Angelo Esposito wants to ask something.
Yeah, hi, Christoph. So I have a comment actually, because unfortunately I won't be able to join the full discussion section. I have other meetings here, but I think I honestly disagree with your interpretation of lambda literally on slide 1, if you want.
On slide 1, give me a sec to go there. On slide 1.
No, sorry. Well, I mean, whatever. When you show the state, the next one, I think. Yeah. There. Yeah. Right. Okay. Exactly. Of course, to some extent, it's a matter of nomenclature, but I think that if we use a confusing nomenclature, it's a problem, because you see, you can have a lambda that is different from 0, even if in your theory, for example, the states H1 and H2 are completely non-interacting, if not through psi 0, okay? Because lambda is a measure of how much your theory is interacting versus free. It's not a measure of whether you are molecular or not. It's very simple to show an effective field theory where you have 3 states, only a cubic interaction, that you get a non-zero lambda.
Look, that's exactly what I tried to say at the bottom of this page. I can also tell you, and I guess you know that well, you can describe the deuteron nicely by just using a theory where some sort of, well, the people who do 3-body calculations, putting in the deuteron really as a pole term, calls it a transvestite field. One can also call it a help field, whatever you wish. Sure. But that what we do here does not mean non-interacting H1, H2. Therefore, you can dream of everything arbitrarily complicated interaction, whichever way you wish. You have to solve some scattering equation to come to unitarity. Otherwise, you cannot compare to the effective range expansion, because that is built on unitarity. And if you then get a pole, near the pole, you can always do a formal field redefinition in quantum field theory that allows you to equivalently rewrite this theory into that theory. And if you then ask what survived from the original theory in the new effective field theory, you see that all physics, non-trivial physics in here goes into the effective coupling, because the binding energy is anyway something we assume from the start. Therefore, whether or not there is some non-trivial H1, H2 interaction in the first place, before we do this field redefinition, all goes into the coupling. And what the Weinberg theory tells us is indeed that this coupling can be directly related to lambda square. Therefore, I very strongly disagree to what you said about that lambda square.
No, but you see, you said it yourself.
This has nothing to do with non-interacting hadron-hadron states.
That's precisely the point.
But it's simply a matter of field redefinitions.
That's precisely the point, meaning since we can always do a field redefinition, lambda doesn't tell you whether H1 and H2 would be interacting and therefore form a molecule. It just tells you that at long distances, there is an interaction with a composite, with a state that can be a tetraquark dressed with continuum, or it could be a molecule. That's the only thing that you learn from long distances.
Okay,
No, I don't agree, but this is for the discussion session, I guess.
We can go to the discussion session and continue with this. Okay, I think Thomas has a question.
Yeah, I have a comment and a question. I've got to correct one statement that you did. You said that, oh yeah, that's a good slide. You said that LHCb constrained DD star to be large. This is not quite correct. We fit constrained relative strength of DD star to rho and omega. So it was constrained on V ratio. There was no constraint relative to this gamma zero, which was supposed to represent everything else. So here, my question comes. I actually personally think that this gamma zero comes out uncomfortably large. If you look at the value given in the paper, it's like 1.4 MeV, which would correspond to pretty sizable branching ratio to other decay modes. And I'm not quite sure that we can find such a large rate in the
Sorry,
other
Tomasz, what is the
decay modes.
uncertainty on that gamma zero?
Well, it is pretty big because, yes, you are right. Yes, the value which was also picked to focus on for EF has a very large uncertainty. So I'm not sure that this was folded into gamma zero error. So you are right, but it is a potential problem not constraining this, because I think what you see here for very small values of EF, G gets very small. So everything gets small except for gamma zero. I think from experimental point of view, it would be great to constrain it.
Yes,
So,
I'm fully with you, Tomasz, and that's what I actually meant when I said the DD star component is constrained to be large. I meant that DD star over this piece here is given some number 3, if I recall correctly. I cannot really remember.
No, it was almost factor of 10.
Or even 10, yeah. Well, actually, what this alludes to is, well, let me first make one remark. G equal to 0 here, and even abandoning these gives just the original Breit-Wigner, and the Breit-Wigner describes the data equally well. Therefore, it's clear that gamma naught cannot be that well constrained from such a fit. Right. Therefore, at the end of the day, we come back on the discussions that we started yesterday in the discussion session, that if you really want to get a controlled extraction of the resonance parameters, and especially the crucial ones here are G1 square and G2 square, or G square if we acknowledge that the X is an isoscalar, what you need to do is to do a combined fit of all possible channels. Therefore, to really constrain G, it requires fitting the DD star channel, a D0 star bar channel. This is the pi J psi channel. This is the 3 pi J psi channel. This is the rest, and the only one we know so far to be sizable is, if I recall correctly, from a BES3 measurement, pi chi c naught. Therefore, and then there are also the vector channels, but they are supposedly much smaller. This gamma J psi, gamma psi prime. Therefore, if one puts all those explicitly here, and in this paper we've provided the explicit formulas to also calculate the rates in the corresponding formulas. If you then do a combined fit to all channels, you get the best refined parameters you can get from a given experiment, and that holds to both. It holds to the LHCb analysis as well as to any Panda experiments that will eventually measure the line shape with much higher resolution. The only way out here is to really do the combined fit of all channels, and the most simple way to evade that is to impose constraints on the ratios of the DD star relative to the other channels where it's known. But since BES3 already measured put the potentially only additional relevant component with the chi-c naught pi, one can put even in an additional constraint similar to the constraints you already put for rho omega.
Right, I think it should be tried. Now, potentially,
Okay.
there is also non-resonant d bar pi. So that's also a question, if this is substantial, because if you look at like Bell paper, they could not really distinguish how much is d star and d star and how much is d pi. So if there was a substantial non-resonant d pi, does this upset this formula, or how should it be modified?
Well, one has to distinguish here if it's dd pi with the d pi or d bar pi in the 1 minus minus or not, right? So if you have interfering what is called background, and you have non-interfering background. If you have interfering background, which means that this is really stuff that comes in exactly the same partial wave, then one can show that the full signal can only be the resonance signal, where this parametrization is sensible, times a polynomial. In the elastic case, this is just what is known as the Watson theorem. But you can even show it for the inelastic case, that if the thing is pole dominated, that the amplitude is still proportional to the pole if you look into the one single partial wave. If there are other partial waves that don't interfere, they add incoherently, they don't upset anything. If you, however, what is possible is that such a formula in the production, if you have additional stuff, needs to be multiplied by the polynomial, but it does not upset the denominator.
I see.
Okay.
I can show you the proof of that. It's not very complicated.
So I think we are quite late. So if there are more questions, let's leave them for the discussion session. And we should now close this session.
Yeah, so
thank you very much.
thanks a lot, Raquel.